Hi guys, good morning.
Good morning.
So only four people, only four of you are there. Shall we wait for 5 minutes? Let your friends join.
Okay.
Yeah. So guys, I gave you a homework, I guess. Did you finish? I mean, I gave you two molecules. I think it was XCO3 and NH4 plus, isn't it?
Yes.
So did you?
I tried, sir, but can you just do NH4 plus one, sir?
You were not able to get for NH4 plus.
Yes, sir.
Okay, fine. Okay. XCO3. Okay, first we'll start. When I talk about XCO3, guys, tell me how many lone pairs, how many bond pairs on xenon? How many lone pairs, how many bond pairs on xenon? Are you there, guys? Hello. There is something wrong. Are you able to hear me, guys?
Yes, sir. We are able to, sir.
Okay. So what I'm asking is, I have XCO3. What is the number? So this was the homework for those of you who joined now. Right? These two are the molecules I gave you as homework, right? So XCO3. First, we'll talk about XCO3. Right. So tell me, how many bond pairs, how many lone pairs on xenon? Oxygen, if I have, how
Sir,
many
three,
bonds would
sir.
it? Three what?
Bond per.
Okay. So you are expecting only what to say? I'm telling. Okay. So basically, what you have to understand is, if I look at the steric number is number of bonding atoms plus number of lone pairs, isn't it? So number of bonding atoms is 3 oxygen atoms. That I understand. Correct. Okay. So what is the number of lone pairs? Oxygen, if I have, between one oxygen and the central atom, how many bonds will be formed? Between one oxygen atom and the xenon, how many bonds will be formed? Only one, Pranav.
Double bonds.
Exactly. So I told you, whenever you see oxygen atom, I am definitely going to have a double bond. So I have 3 oxygen atoms with xenon. So all the 3 oxygen atoms with xenon, I'm going to have a double bond getting formed, isn't it? Right. Okay. So if that's the case, right? So xenon has how many valence electrons? Xenon has 8 valence electrons, completely filled octet, noble gas configuration, isn't it? So out of that, there are, okay, for 2 oxygen atoms, there are going to be 2 electrons gone, because there are going to be double bond, 2 electrons coming from xenon, 2 electrons going from oxygen, making a double bond. So this is how the this thing say 1, 2, 3, isn't it? So you can see 1, 2, 3, 4, 5, 6. 6 electrons are gone in all the 3 double bonds, isn't it? So how many lone pairs now?
One lone pair.
One lone pair, totally 8 electrons, 6 are involving in bonding. So definitely I'll have 2 electrons left out. So one lone pair. So 3 plus 1 is 4. So obviously the hybridization is sp3. Okay, cool. So now we can go for the orbital diagram, right? By hybrid orbital diagram we can go. So now you have to account for, so what do you have to account for? You have to account for how many sigma bonds here? How many sigma bonds here? 3 sigma bonds, and there is one lone pair. So all these 4 things, that is 3 sigma bonds and 1 lone pair, should come inside the hybrid orbitals. And obviously the hybrid orbitals are going to be sp3 hybrid orbitals, right? And I have to account for 3 more things, that is 3 more pi bonds is what I have to accommodate. So obviously what will you see? You will see after the hybridization, you will see that I'm going to have 3 unpaired electrons. If you get that, you are absolutely right. So we'll see whether we get that. So Xc, okay, first of all, we need to know the electronic configuration. No, it's simple. If you know the periodic table, it's very simple. So starting with noble gases, I have helium, you leave helium, right? After that, I have neon, argon, krypton, xenon, right? Neon, argon, krypton, xenon, radon, all these are the noble gas elements, isn't it? So look at this. Helium comes under first period. That is next. Neon comes under second period. Helium, neon, argon comes under third period. Krypton comes under fourth period. Xenon comes under fifth period, right? So now what will be the configuration for xenon then? Valence electronic configuration. What will be the valence electron configuration for xenon if it is in fifth period? Fully filled configuration. So what do I have? Is everyone so sleepy or you don't know the answer?
Sir, is it 4D10 5s2 5p6 that ending?
Exactly, that's what, right? So please understand, guys, if I have a noble gas element, right? If I have a noble gas element, the valence electron configuration would be ns2 np6, fully filled configuration. ns2 np6, where n is the period number, and obviously before this you would have had your halogens, that is fluorine, bromine, chlorine, iodine and all that. So there what would have been the configuration? ns2 np5, isn't it, right? So please remember that the valence electron configuration for your any noble gas element will be ns2 np6, where n is the period number. So hope you understand, guys. Periodic table, if you remember, there are a lot of things that are going to be easy. If you don't know what you have to do, you have to remember the atomic number for xenon, you have to write the electronic configuration so much and then find it out. Okay, it is going to be ns2 np6, and in this case it is in the fifth period, so obviously the configuration is going to be 5s2 5p6, fully filled configuration, 5s2 5p6. And obviously if I have fifth shell, do I have a d subshell also? Yes, I have a d subshell.
Yes,
So that d subshell is empty, 5d0. No problem. That's for xenon. Done. Okay. So now let me draw the ground state configuration. Why are the markers like this? Okay. So let me draw the ground state configuration for xenon. So I have 2 electrons in 5s, 6 electrons in 5p. 1, 2, 3, 4, 5. So this is my 5s, 5p, 5d. All these are my orbitals in ground state. Yes? Okay. Cool. So the thing is, what I was saying. Okay, so we are talking about the ground state configuration. Now we'll talk about the excited state configuration. So in excited state configuration, what will you do, guys? In excited state, what will you do?
transfer electron to the
So
empty
all the paired electrons should be transferred to the empty orbital, right? All the paired electrons should be made unpaired by shifting all the electrons to the empty orbital. Here the only empty orbital I have is 5d. There's no doubt about it. It's because 5s is fully full. This thing 5p is full. So the only empty orbital in the valence shell is obviously going to be 5d. Correct? Okay. So obviously I'll have 1 electron, 3 electrons. So 1, 2, 3, 4. 4 electrons will be in 5d. Cool. Right? Okay. So I know the hybridization is sp3. Isn't it? The hybridization is sp3, we just found out with the help of your steric number. Correct. So in the I'm going to have 4 sp3 hybridized orbitals, obviously. So how many sigma bonds I had? I had 3 sigma bonds, and one more is what?
1 lone pair.
Correct. So in the 4 hybrid orbitals, 3 sigma bonds will be there and 1 lone pair will be there. So when you're going to mark the hybridization, you have to make sure that inside the hybridization there is 1 lone pair. Correct. So I'll just remove this electron, the last electron, and put it here. Just making sure that inside the sp3 hybridization, look at this, sp1, p2, p3. Inside the sp3 hybridization, there is 3 sigma bonds, 1, 2, 3, and there is a lone pair. No problem. So I would have had 1, 2, 3. That is sp3, sp3, sp3. Sorry, 4. 4 numbers of sp3 hybrid orbitals. In 3 of them, I have an unpaired electron. In the 4th, I have a lone pair present. And obviously, I have 3 oxygen atoms. Done. Okay, so you have accounted for 3 sigma bonds and 1 lone pair. So what else I have to account for? I have to account for 3 more pi bonds. What did I tell you? After the hybridization, the number of unpaired electron is what is my hybrid number of pi bonds. So you see that there are going to be 3. There are going to be 3. What is the unpaired electron after the hybridization? So obviously I'm going to have 3 pi bonds. Understood?
Yes, sir.
Okay. How many of you tried this?
I tried, sir.
Rohan
tried,
told
sir.
he tried.
I tried.
Right. Good. Shruti tried. Who else?
I tried, sir.
Divya. Yeah, Divya tried. Okay. Anybody else?
I
Sana.
sir.
Who Kanna? Venisha tried. Is it Venisha? Who
Yes,
tried?
sir.
Okay. Good, Kanna. Good. Right. So what about others? Guys, you have to try. Right. It's how much time it took? 1 minute, 2 minutes. I'm explaining and then I'm doing. If you're doing it by yourself, it'll take only less than 1 minute for you to get these answers. Okay. So anyways, so this is how the orbital diagram looks for XCO3. Okay. So let me go for NH4 plus. Right. Okay. And before that, what is the shape and what is the geometry of this molecule? Shape will come. Okay. Shape will come later. But tell me the geometry of this molecule. What is the geometry?
Tetrahedral.
Correct, right? So geometry here is tetrahedral. By the moment you see sp3 hybridization, I'm going to have tetrahedral geometry. Now the geometry will change. Geometry will be same or different depending on whether I have lone pair or not. Isn't it? Geometry will be different or same depending on whether I have a lone pair on the central atom or not. Here, yes, I have a lone pair. So definitely geometry and shape are not going to be same. Okay. So the shape is going to be something called pyramidal shape. This is how it's going to look. So hope you've taken this down, guys. And have this part. Or no problem. I'll just take the first thing. It's enough for me. So you would have had XC. Now, if at all it is tetrahedral, you know how the shape looks, isn't it? So you know a dashed. I would have. Okay, if it is tetrahedral. This would have been my tetrahedral shape, isn't it? One bond coming towards you, the dash represents that bond is coming towards you, the wedge is coming towards you, the dashed line is going inside the plane, right? So this is what is tetrahedral shape. But here, what happened is I have just removed removed a bond pair, and I have removed a sigma bond or a bonding atom, and I have put a lone pair. So it is no more going to be tetrahedral shape, this shape is going to be called as pyramidal shape. This shape is what is called as pyramidal shape, or you can even call it as trigonal pyramidal shape. It's called as trigonal pyramidal shape. Okay, so you can see that it's like a pyramid, isn't it? Like it's like three things are coming, and at the top I have a lone pair. So you can see it's a trigonal pyramid. Okay, right? Okay, so I can now, this is all about, so the shape of geometry of XeO3 is tetrahedral, shape is trigonal pyramidal shape, right? So we'll do it for NH4 plus, we'll see what happens. So what was the bond angle there in tetrahedral, guys? What was the bond angle in tetrahedral?
109 degrees, 5 minutes.
Exactly, right? So the tetrahedral bond angle was 109 degree, 5 minutes. But here, since I have a lone pair present, what will happen? I'll have lone pair, bond pair repulsions, this side, right? So the bond angle will be very less. Bond angle would be, would have got constricted because of the lone pair, bond pair. We saw VSEPR, right? So what does VSEPR says? VSEPR says the most stable shape will be in such a way that the repulsions between the electrons are minimum, right? What are the type of electrons I have? Bond pair of electrons and lone pair of electron, and between them I can have three different types of repulsion. lone pair, lone pair, lone pair, bond pair, and bond pair, bond pair. Among them, lone pair is the highest, and bond pair is the lowest. So here you see lone pair, bond pair repulsion. So obviously that is going to make the bond angle to be lessened. Okay, cool. Now we'll go for NH4 plus. What is wrong with these markers? Okay, better. So I have NH4 plus. Okay, guys, there are two ways of looking at this. Okay, first way is, okay, when I looked at SO42 minus sulfate ion, right? What did I tell you about negative charges and positive charges? Do you remember? When I looked at SO42 minus, that is the first ion you saw for hybridization, isn't it? So there was a negative charge. Here I have a positive charge. But for both positive and negative charges, I told you where to put the positive and negative charge. Do you remember that? Just turn your pages and see what I have given there.
So you told to give a negative charge to the more electronegative.
Correct. So again, I'm repeating, this is a general rule, right? So the thing is, when I have a negative charge, that has to go to the bonding atoms, or I would say it has to go to the more electronegative atom, right? It has to go to the bonding atom generally, or it has to go to the more electronegative atom. So in SO42 minus, obviously I know oxygen is more electronegative and it is the bonding atom. So I gave the 2 minus, -1, -1 to 2 of the oxygen atoms. That I did, right? Now in this, okay, when I talk about the positive charge, you have to give it to the central atom, or I would say less electronegative atom. Isn't it? The positive charge has to be given to a central atom, or it has to be given to the less electronegative atom. Okay. Now there is a complication here if you look at it. Right. What is the, can you tell me, can you look at this statement, that is the positive charge statement, and you'll see what will be the problem in this molecule NH4 plus. Are you able to understand my question? I'm telling positive charge has to go to the central atom or the less electronegative atom, right? Now in NH4 plus, there is a problem if you use this rule. Like there will be an ambiguity which will be coming. What is the ambiguity? What is the electron? Which is more electronegative, nitrogen or hydrogen?
Nitrogen.
Nitrogen is more electronegative, right? Okay, so that means hydrogen is less electronegative. So hydrogen has to get the positive charge. But if I go by this, the central atom has to have the positive charge. Okay, that means what? Nitrogen should have the positive charge. So right, if I go by central atom rule, positive charge, that means nitrogen should have the positive charge. And if I go by the next one, that is less electronegative atom should have the positive charge, hydrogen should have the positive charge. So which should we take is the question now. Okay, so here you can take any of it. The answer is you can take any of it, but the orbital diagram is going to be a little different. We'll see both of them. We'll see what happens. Okay, so let me put first nitrogen is having the positive charge. Okay, I'm putting the positive charge on nitrogen first. We'll see what happens. Okay, fine. I think you will be able to do it. Guys, can you do it? Go for the orbital diagram. I have nitrogen to have a positive charge. Fine. First, before all this, what is the hybridization? Hybridization. What is the number of bonding atoms?
4.
4 bonding atoms. Okay, so steric number is equal to 4 plus. Do I have any lone pair on nitrogen? Think about it. Like just look at this. I have N plus, correct? Right? So if I have N plus, so nitrogen had 5 valence electrons, 5 only? Okay, 5 valence electrons. So if it is N plus, how many valence electrons it will have?
It will have 6, sir. So 1 lone pair.
6.
4, sir.
4, sir.
4. Correct, exactly. I think it was a slip of tongue. So it is 4 valence electrons, and obviously they see that there are 4 hydrogen atoms. So definitely there are going to be 4 sigma bonds. What is the lone pair? Number of lone pairs?
0, sir.
Obviously.
No lone pair.
Exactly, Kana. So 4. What is the hybridization now? Easy. sp3 hybridization. Go for it. Tell me. Go for the orbital diagram. I'll give you just 1 minute. Quick. Go for it. So put the positive in nitrogen. So that means there are only 4 valence electrons. So there are no lone pairs, there is no pi bond, just sp3 having 4 unpaired electrons. That's it. Very simple. I think you would have got it, right? So nitrogen would have had 2s2, 2p3, right? But N plus would have had 2s2, 2p2. Correct? 2p3 should have been there, but since it is N plus, it is 2p2, 1 electron removed. Right? Say in your ground state, 2s, 2p having 2 electrons. Now what will happen? This electron will be shifted here. So in the excited state, 1 electron here, 3 electrons there, and that's it. sp3 hybridization, so 4 numbers of sp3 hybrid orbitals, and each hydrogen atom will give 1 electron, making 4 sigma bonds. Done. Right. Now in this case, you took nitrogen atom to have a positive charge. Okay. What if hydrogen atom is having the positive charge? Right? What if hydrogen atom is having the positive charge? Now, for you to understand this, right, for you to understand what will happen if I have hydrogen to have a positive charge, and actually in reality, right, so obviously in reality only one of them should be correct. Either nitrogen should have had a positive charge and hydrogen should have had a positive charge, but by theory of hybridization you are able to get, well, like you can get the gist of what is happening. But in reality, which is true, whether nitrogen will have a positive charge or hydrogen will have a positive charge, the answer is hydrogen is the one which will have positive charge. Hydrogen is the one which will have positive charge. Okay. Now, how do I prove it to you? Right? Is because, guys, do you know that ammonia can act as a base? Do you know that?
Yes, sir.
Okay, so everybody knows that ammonia can act as a base. In technical terms, ammonia will act as a Lewis base, or I would say it is going to act as a Lowry-Bronsted base. Do not worry. Whatever the terms I told you, you will be studying it in this chapter. In the chapter of equilibrium, you will be studying it. Okay, so don't worry. So what I'm trying to tell you is, now in this case, we will not go much into it. So please understand, a base is something, right? A base is something which can give OH minus when dissolved in water. That I know, isn't it? But there is one more way by which you'll be able to visualize base. The base is one which will be able to accept H plus, right? So base is one which will be able to accept H plus, and so the two ways by which you'll be able to account for a base. One is it can donate H plus. Sorry. It can donate OH minus, or it can accept H plus, isn't it? So ammonia being a base will accept H plus to form NH4. Right? Ammonia is a base which will accept H plus to form NH4 plus. That's why I call ammonia as a base. Okay. So it is pretty much understood that definitely hydrogen is the one which is having the positive charge. And go by logically speaking also, hydrogen is more electropositive. So definitely that should have the positive charge. Okay. But how are we going to account? How are we going to draw the orbital diagrams? Or first, if I can draw the Lewis dot structure itself, that is actually going to be a very good information for this. Okay. So we'll try to draw the Lewis dot structure. Okay. Fine. So we will draw two Lewis dot structures. One for nitrogen having the positive charge, and other for hydrogen having the positive charge. Okay. Say now nitrogen having the positive charge is very easy, isn't it? So I know I'm going to have four electrons in the valence shell, 1, 2, 3, 4, with the positive charge on nitrogen, right? And there are 4 hydrogen atoms, each having 1 electron. So done. Hydrogen requires 2 more electrons to satisfy its octet. So 4 hydrogens are done, right? And nitrogen already is having 4 valence electrons. It requires 4 more electrons to satisfy its octet. So it will take all the 4 electrons from 4 hydrogen atoms. Done. Very simple, right? This works, right? But if I put H plus, if I put hydrogen to have the positive charge, we'll see what happens. So what I can understand is, there are 4 hydrogen atoms, right? There are 4 hydrogen atoms. Out of them, only 3 are, out of them 3 are hydrogen atoms, and one of them is a hydrogen ion. H plus ion is there. So one of the hydrogen is going to have a positive charge. Out of the 4 hydrogen, one of them is going to have positive charge. So I know hydrogen is already having only 1 electron. Correct? Hydrogen atomic number is 1. It has only 1 electron. So if I say H plus, that means there are no electrons at all. Yeah, there are no electrons at all, right? Okay, fine. So now nitrogen is now having 5 valence electrons, because nitrogen is not having the positive charge. So nitrogen is having 5 valence electron, 1, 2, 3, 4, 5. No problem. Now I'll take the normal hydrogens. So hydrogens will have the electrons, and H plus has no electron. I'm not putting any electron there. Okay, these are done. No problem. Okay. What do you think is going to happen, guys? For the fourth H plus, that is the H plus and the nitrogen, what is going to happen?
A coordinate bond.
Wow, yes, that's the answer, right? So here it's going to be a coordinate bond, people. So here these two there's a lone pair, and this lone pair will be donated to the H plus. Cool. So how will I draw the bonding diagram? So I have basically a coordinate bond going from nitrogen to hydrogen, and all the other three are okay. Right? All the other three are okay. Right? Cool. Still the hybridization is same, the shape is same, geometry is same, everything else is same. But you can see that there can be two different structures. Where else did you see two different structures? For which ion, if you can remember? There was one more ion. For that, I had two different structures, Lewis-Strauss structures. What was that?
N3
No. It was SO42 minus, if you can remember. Right? So without a coordinate bond, I'll be able to draw structure. With the coordinate bond also, I'll be able to draw structure for SO42 minus. Okay. So anyways, so this would, okay, this is H plus, right? So this would have been the structure for NH4 plus. Okay, fine. So if I'm going to draw the hybridization for this particular thing, it is going to be little, that we already saw. It's very simple, right? So here, can you try, guys?
Yes.
Okay, actually it is not going to be different. I'm sorry. It is going to be exactly same. Except, one second. So what would have happened is, okay, so actually this is a problem with hybridization for people, right? So if you try to draw the hybridization, you will find it little not working, right? So we'll see what happens. Okay, so again nitrogen, 2s2, 2p3, valence electron configuration. So 2 electrons. Okay. Now even if I shift, there is no 2d. 2d is not there, right? So you cannot shift it there. So there is no point in shifting, but still we'll shift. No problem. Okay.
Okay, sir.
Can you form sp3 here? I know the hydrogen is still sp3, right? I can form sp3. It's not like you should not form. I have an sp3, no problem. But does it account for 4 sigma bonds?
No, sir.
Why? You can still see that there is a lone pair here. So what is exactly happening is this lone pair is not there. It has been donated to the H plus. That's what you need to understand.
Okay, sir.
Okay. So anyways, so if at all these kind of complications come, so in hybridization, people, right? In hybridization, blindly go for this. Positive charge, central atom, negative charge, bonding atom. Blindly go for it. Okay. But in reality, it might be different. Right? In reality, it might be different. But so remember, positive charge, central atom, negative charge, bonding atom. This is the rule which you have to remember. Not more electronegative, less electronegative will make it more complicated. Okay, so positive charge, if you see in an ion, polyatomic ion, it has to go to the central atom. If you see a negative charge, it has to go to the bonding atom. Okay, fine. So what is the shape and the geometry here, people?
Geometry is tetrahedral, sir.
Tetrahedral.
Shape?
Trigonal pyramidal?
Why?
Because there's a lone pair, no, sir.
Oh, this is not the thing. What was the thing which you saw there in the previous hybridization? Did you find any lone pair there?
Oh, no, sir.
So what is the shape then?
Tetrahedral.
Exactly. So here both the shape and the geometry is going to be tetrahedral because there is no lone pair. At least according to your what is that? Theory of hybridization. Even in reality, I don't have a lone pair. It's actually in the form of a coordinate bond. So guys, yes. So the shape is the shape and the geometry both are tetrahedral. Okay. Fine. Now one last example. Okay, not one last example. There are two more examples. Fine. Now you are going to do this molecule, ammonia. Go for it. First, hybridization. Before hybridization, number of bonding atoms, number of lone pairs, then hybridization. Then you have to go for what is that? The orbital diagram. Account for the sigma bonds, account for the lone pairs, account for the pi bonds if any, and the shape and the geometry. All these things should come. So guys, okay, I'll just go do the first step. So steric number is what here?
4.
Okay, so there are 3 bonding atoms, 3 hydrogen atoms are there. Okay, so I know nitrogen is having 5 unpaired electrons, 5 valence electrons. So 3 are involving in bonding. There are 2 electrons left, so that is 1 lone pair. So 3 plus 1 is 4. So again, sp3 hybridized. Okay, go for the orbital diagram. Now please understand that you have to account for 1 lone pair, and that lone pair should be inside the hybridized orbital. So I think it's very easy. Nitrogen, 2s2, 2p3, 2s having 2 electrons, 2p having 3 electrons, and I have to. And there is no way to shift to the next higher. I mean, next in the there is no empty shell, so I can shift it to the last one, whatever is available for me. That's it. So this is my sp3 hybridization, sp1, p2, p3, right? So there are going to be 3. And there are going to be 4 sp3 hybridized orbital, 3 of them having 1 electron, and the 4th one is having a lone pair. No problem. And obviously there are 3 hydrogen atoms. So where is the red one? Oh, here. So I have 3 hydrogen atoms giving 1 electron, making 3 sigma bonds. Okay. How many of you got this?
Got, sir.
Got, sir.
What about others? What about okay, what about Abhishek, Mithun, Pranav, Surya Mithu, Venisha? Okay, good. Right? So I think most of you would have gotten it. Okay, now tell me, shape and geometry. Shape and geometry.
Geometry is tetrahedral, sir.
Okay,
Shape is trigonal pyramid.
that's it. Very simple, right? So the geometry is tetrahedral. Moment you see what is that sp3 hybridization, blindly you will put the geometry as tetrahedral. And because I have a lone pair, the shape is going to become trigonal pyramidal. Right? Done? Okay. Fine. One last example in sp3. We'll go for the next hybridization. You are going to do it for H2O. Go for it. Do it for H2O. Now, did you see? Okay, first you do, I'll tell you. How many lone pairs on oxygen, people?
2 lone pairs.
2, sir.
Exactly. Right. So oxygen is having 6 valence electrons. Out of that, 2 are involving in bonding. So 4 electrons are left. So 2 lone pairs. So 2 bonding atoms, 2 lone pairs, sp3 hybridization. Now, like the only difference between last case and this case is that what? I'm going to have 2 lone pairs instead of 1 lone pair. That's it. So steric number is 2 bonding atoms plus 2 lone pairs, which is 4. Again, sp3 hybridization. Right. So now we'll account for it. Okay. So oxygen is having 2s2, 2p4. Right. So in ground state, 2s, 2p4. So I'm following Hans rule. Okay. So again, there is no 2d. 2d is not there. So now I have 2 unpaired electrons. So I can shift, say, if you want, you can shift or you can keep it just like that. Say this electron goes here, this electron goes here. Done. Now I have sp3 hybridization, sp1, p2, p3, right? So I have 4 sp3 hybridized orbital, 2 of them having single unpaired electrons, and 2 of them are having lone pairs. And I'm going to have 2 hydrogen atoms giving 1 electron. Simple, right? Very, very simple. Okay. Now the question is, what is the shape and geometry? Okay, first we'll talk about geometry. Geometry is
Tetrahedral.
tetrahedral. Done. A moment you see sp3 geometry is tetrahedral, no problem at all. But the shape is going to be different. Okay. So now these kind of molecules, I'll be able to draw the general structure as AB2L2. That is 2 bonding atoms and 2 lone pairs. Right? Last time in NH3, what you saw? AB3L, 3 bonding atoms and 1 lone pair, isn't it? In this case, I have the molecule to be in the form of AB2L2, right? So now, if I try to draw the shape, okay, so I have 2 lone pairs present now, right? So this is the first time, people, you are visualizing a lone pair repulsion, is it not? So till now you would have seen bond pair, or say lone pair, isn't it? This is the first time you are seeing lone pair repulsion, because there are 2 lone pairs in the central atom itself, isn't it? So these 2 lone pairs itself will be very far away from each other, because I know lone pair repulsion is the maximum in all the 3 types of repulsions, isn't it? So already these 2 lone pairs will be very far away from each other, And if they are far away from each other and both the sides I have my bonding atoms also, right? Both the sides I have my bonding atoms also. So obviously the lone pair bond pair repulsion also will become higher because these two are going apart, right? These two are going apart. So definitely this and this will still more go apart. Like the bonding atoms will still come closer, right? So now this shape, if I just exclude this, if I just exclude the lone pairs, what is the shape do you see, people?
Trigonal.
Oi, how is it trigonal? There are only two bonding atoms. How it is trigonal?
Linear.
Linear, sir.
Ah, okay. Okay. This is not linear. Linear would have been prospect 180 degrees. If it is little like this, what is it called as?
Bent.
That's it. Yes. Answer is again bent or V-shaped. Okay. So remember, whenever I have AB2, L2, for one more also we saw a bent. What was that? For what type we saw bent? Simple, right?
SP2.
Instead of having two lone pairs, if I have one lone pair, still it is bent, isn't it? So you would have seen AB2L type of molecule. That example would have been NO2, NO2 minus, right? So that would have had this kind of bent. So people, like in sp3 hybridization itself, right? The moment you see sp3, geometry is similar. Geometry is tetrahedral, but the shape is going to. There are going to be three different types of shapes, right? So we'll see what are they. Right. So when I have AB4, I'm talking about the shapes. Shape is here tetrahedral. When I have AB3L, here it is trigonal pyramidal. And lastly, when I have AB2L2, here the shape is bent. So in sp3 itself, sp3 hybridization itself, I would have had, what is that? Three types of shapes. Okay. Now I'm going to ask you a question. We'll see how many of you answer. Okay. I have CH4, I have NH3, and I have H2O. Arrange them in the order of bond angles. Which is having maximum bond angle, which is having minimum bond angle? You tell me. Okay, first, bond angle of CH4 can be directly found out. What is it?
109 degrees, 5 minutes.
Exactly, 109 degree 5 minutes, because there are four bonding atoms, zero lone pair. This is of the type AB4. So definitely tetrahedral bond angle, 109 degree 5 minutes. Okay. So for NH3 and H2O, we will not be able to tell the number, but at least I'll be able to compare, isn't it? Now in NH3, what happened? I have a tetrahedral shape, right? In one of the bonds, instead of a bond, I have a lone pair. So what happened there? Because of the lone pair bond pair repulsion, the bonds got constricted, isn't it? So can I say that NH3 will definitely have lesser bond angle than CH4? Can I say that?
Yes, sir.
Right.
Yes,
So
sir.
because the bonds are getting constricted because of your lone pair bond pair repulsion. So definitely NH3 is going to be greater. Okay. Now when I compare NH3 and H2O, people, look, you can look at here. There are two lone pairs, right? There are two lone pairs. These two lone pairs will go far apart, thereby making the bonds again coming more and more constricted. There I had only lone pair bond pair repulsion. NH3 I have lone pair bond pair. Here I have lone pair repulsion. That is still more greater, right? So the bond angle will still more reduce. So definitely H2O is the one which is going to have the least of all bond angles. Okay. So if you want the correct numbers, NH3 will have a bond angle of 107 degrees. H2O will have a bond angle of around 104, 105 degrees. This would have been the bond angles. Okay. Everybody understood why the bond angles are like this? Everybody should give me a yes. Please
Yes,
give me a
sir.
yes.
Yes, sir.
Yes, sir.
Okay. Okay. Cool. So hope everybody understood how the bond angles are changing. Cool. Now we'll go for the next hybridization. Okay. Fine. We'll go for sp3. What is the next hybridization? Do I have an sp4? Guys?
No.
What is the next hybridization then?
SP3D.
SP, correct. So SP is over, SP2 is over, SP3 is also over. So now we are going for SP3D because there is no SP4. There are only 3 p orbitals. Right? So SP3D we are going to take. Oops. Oh my god. Guys, wait. Problem happened. Okay. Yeah. So we'll see. We are going to see first in steric number is 5 sp3d hybridization. So again, I can have so many different types here. So how I had in sp3 itself, I had ab3, ab4, ab3l, ab2l2. Here also I can have so many different types. Right. So first we'll start with the easiest one. So we'll start with ab5. AB5 type of molecules. What do you mean by this? There are 5 bonding atoms and no lone pairs. Okay, fine. So let me take an example. Example is PCl5. Example is PCl5. Okay, cool. Now, we are going to do for phosphorus. Phosphorus belongs to which family? Guys, phosphorus belongs to which group? That means it belongs to which family?
Nitrogen.
Exactly. So it belongs to nitrogen family. Guys, if you don't know periodic table, it is going to be very difficult. Now itself I'm telling. Okay, fine. So phosphorus belongs to nitrogen family. Okay. Now, if at all you don't know, you have to remember the atomic number for all the elements. Like it's impossible. Even I don't remember like that. Okay, I remember the periodic table. I know which below which element it comes. That is an easier way because I'll be able to directly get the balanced electronic configuration. Right? That's what is required here. Cool. So phosphorus is having it belongs to nitrogen family. So nitrogen is having 2s2 2p3. Now this would have had 3s2 3p3. Next, right? Next after hydrogen, right? Nitrogen is having 2s2 2p3. This will have 3s2 3p3. No problem. Okay. Now, and I have a 3d also because it's now the third shell. Now I have a d orbital also. So I have a 3d also, but which is empty. Okay, right. Now I'll go for the ground state and excited state. Okay, no problem. Now what I have to do? I have to shift the electron to the empty orbital. Now you see here I have an empty orbital. D orbital is still empty, right? So I can shift this here. Okay, so I have 1 electron, 3 electrons, and 1 electron. Yes. Okay. Okay. Actually, we didn't talk about the hybridization, so you can easily understand the steric number here is 5 bonding atoms, and there are 5 valence electrons, and all of them are involving in bonding. 5 valence electrons, all of them are involving in bonding, so 0 lone pairs. So it is 5, so sp3d. That's understood. So now you can see that S, P1, P2, P3, and D, sp3d hybridization. You can see S, P1, P2, P3, and a d orbital. Okay, right? So now how is it going to be? Now I'm going to have 5 numbers of sp3d hybrid orbitals, each having 1 1 1 1 electron. Okay, and then I'm going to have 5 chlorine atoms, all of them giving 1 1 1 1 1 electron. That's it. 5 sigma bonds are formed. Okay, cool. So this is how hybridization is done. So the next question is, what will be the geometry? What will be the shape? Right? Okay, guys, I'll tell you here itself. When at the moment you see sp3d hybridization, okay, I'll not make you just mug it up. I'll tell you the logic behind the shape. Okay. So fine. Have you taken this down?
Yes, sir.
Right. Okay. Okay, so let me take AB5. Okay, so now I have to make sure that I have to put 5 bonding atoms. I have to put 5 bonding atoms. Okay, so this is how it's going to be, right? The shape is going to be called as trigonal bipyramidal. You remember trigonal pyramidal? That is for 4. Right now it's very easy, right? So here, look at this. I'm going to have 2 types of bonds here. I'm going to have 2 types of bonds, or speaking in what to say, speaking in more depth, speaking in more technically, right? So in sp3d, people, right? In sp3d, actually I can see that it is going to be a combination of 2 different mixing, right? 2 different hybrid orbitals are there in sp3d itself. How will I be able to look into it is, I'll be able to write sp3 as sp2 plus pd. Are you able to understand? Right? I can write it as sp2 plus pd, making it sp3d. Okay. So how can I tell now? If I know that I'm going to have 5 numbers of sp3d orbitals, so I obviously know when I have sp2, that is 1 s orbital and 2 p orbital combining, I will have 3 numbers of sp2, and I will have 2 numbers of p and d, like 1 p orbital, 1 d orbital are combining to form pd hybridization. But like overall, we'll not speak about all this. But why am I telling this is because the shape is going to be in such a way. Okay, so please understand, sp3d is a combination of 2 different hybridizations. One is sp2 and the other one is pd. Other one is pd. Okay, now if that's the case, right, till now whatever you have seen, like say I have sp3, I have 4 bonds, or say in sp2 I have 3 bonds, all the 4 bonds or 3 bonds, whatever is, I'm going to have same bond length. What do you mean by bond length? The distance between the nuclei of the bonding atom and the center atom, right? I'm going to have same bond length, or say the same bond strength, whatever it is. Okay, but here you can see that 3 of the hybrid orbitals, that is that is sp2, 3 of them are going to have, say, different strength than when I compare to your pd hybridization. Okay, so what you have to understand is, depending on sp2, there are 3 sp2s, I'm going to have 3 bonds, and depending on pd, there are 2 pds, there are going to be 2 bonds. Okay, so what I can understand from this is that if I have AB5 or say PCl5 type of molecules, there are going to be 3 bonds. There are going to be 3 bonds which are going to follow sp2, and there are totally 5. 3 are gone, and 2 more are going to follow pd. Right? Okay. Now let me ask you a question. Right? Which do you think is stronger, sp2 or pd?
sp2.
No doubt about it, right? When I know s orbital is spherically symmetric, right? S orbital is spherically symmetric, so obviously the effective overlapping is going to be very, very, very high when compared to p and d and all, right? So definitely, the sp2 hybridized bonds are definitely going to be stronger than the pd hybridized bonds. Okay, so definitely I'm going to have 3 bonds which are shorter. Why short? Because whenever the bond strength is high, that means the atoms will be very, very close to each other, very strong overlap, right? The bond length is lesser. And obviously when I go for PD, not much of a strong bond, so the bond length is going to be little bigger. Okay, right, fine. Now when I had sp, now forget about this PD, when I had sp2 hybridization, what was the shape?
For
When I had
SP2, sir.
for sp2, yeah, for sp2, what was the shape or what was the geometry? Hmm? Do you remember BF3?
Yes, sir.
What is the shape?
Trigonal
Trigonal.
planar.
Correct. So it is going to be trigonal planar with a bond angle of 120 degrees. You hope you remember that, right? So AB3 you would have had something like this. So it's a trigonal planar and the bond angle is 120 degrees. You would have seen this. Okay. So yeah, so this is what is there for sp2, right? So for AB5 also, 3 of them are going to be in trigonal planar shape, right? 3 of them are going to be in trigonal planar shape. Okay. Now say, look at this. I have P and D coming together, or let me consider it as 2 orbitals. Okay. Let me consider as 2 orbitals. Like if it was sp, if it was s and p, what would have been the shape? It would have been sp hybridization instead of pd. If it was sp, what would have been the shape?
Linear, sir.
Linear. Wonderful, right? So so this basically I'm going to form a linear shape, and this is actually going to form a trigonal planar shape, and the total shape of the molecule is a combination of these two. The total shape of this molecule is going to be a combination of trigonal planar and being linear. Okay, so now in AB5, you have done all the things now. The shape is going to look like this. So I'm first to talk about the trigonal planar. Okay, so 1, 2, 3. So this is my planar region, or in other words, I can tell it like this. Say 1 is going on this thing, or no, not required. So I can just put it like this, right? This is my trigonal planar. No problem. Okay. Now trigonal planar is done. Now I have to account for the linear shape also. Isn't it? I have to account for the linear shape also. So 1 here, 1 here. So this is my linear. So linear, trigonal planar, B, 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 and B. Okay. Fine. So now we cannot call it as trigonal, planar, and linear. We have to call it as a single name, right? So what you understand is there is a trigonal, there is a triangle, right? On top of the triangle, there is one thing. On bottom of the triangle, there is another thing. Okay. So please understand, I am going to call this particular shape. I don't have a space. I will write it here. This particular shape is going to be called as trigonal bipyramidal. Hope you understand why it is bipyramidal. So you can see 1, 2, 3, 1, 2, 3. There is going to be a big pyramid like this. One on top, one on bottom. So 2 pyramids. So there is going to be a bipyramidal, and I have a trigonal shape also. So it is going to be called as trigonal bipyramidal shape or geometry. Okay. Everybody understood? Please give me a yes.
Yes, sir.
Yes, sir.
Yes, sir.
Good, good. So please understand that sp3d hybridization is a combination of trigonal, planar, and linear, giving it trigonal bipyramidal shape. Okay. So guys, we are out of time. So we'll speak about this more in the next class. Okay. Fine. Until then, we'll see. Thank you. Bye bye.
Thank you, sir.
Yeah. Thank you.
Thank you.
Thank you, sir.
Yeah. Thank you.